Hello everyone, today we will be discussing stroboscopic motion, a presentation done by Group B. We will cover an introduction to the stroboscopic motion, the experimental procedures, the experimental results, and conclusion. So what is the stroboscopic effect? The stroboscopic effect is a visual phenomenon characterized by a change in motion perception induced by a light stimulus, the luminance or spectral distribution of which fluctuates with time, for a static observer viewing a moving object within a particular frequency. As a warning, the strobe effect can induce epileptic seizures in predisposed persons, and this effect will be shown in this video. How does this effect work? Because of temporal summation and visual persistence, brief retinal stimulations produce neural activity that lingers for a short duration. When the illuminance flickers, as with the strobe light, the retinal image becomes temporally modulated, and if the persistence of time of the visual system is shorter than the period of light modulation, the visual system resolves individual illumination pulses, leading to aliasing in perceived motion, causing the object to appear frozen, slowed, or moving in the opposite direction, depending on the relationship between the modulation frequency and the object's motion. What is the role of frequency? In the stroboscopic effect, frequency determines how often the moving object is sampled by the visual system. The modulation frequency of a light, its flicker rate, acts as a sampling rate. If it matches the object's motion frequency, the object can appear stationary. If it is slightly lower or higher, the object appears to move slowly forward or backward due to aliasing. If the frequency is too high for the visual system to resolve individual flashes, shorter than visual persistence, the motion becomes blurred instead of stroboscopic. The first part of the procedure was a stroboscopic effect demonstration using water droplets. So firstly, the stroboscope was set up near a dripping water faucet. The water was allowed to drip continuously from the faucet, and the strobe light was turned on and aimed at the falling droplets. The strobe frequency was slowly adjusted while observing the droplets, and the different effects produced were observed as droplets appearing to slow down, droplets appearing stationary, droplets appearing to move upward back into the faucet. The frequency was being continuously adjusted until it was comfortable operating the stroboscope and recognizing the effect. Observations of the droplet motion with and without the strobe light were all recorded. The second part of the procedure was stopping a fast-moving object, edger wheel. Firstly, the white line on the surface of the edger wheel was located, and the edger machine was then switched on so that the wheel began rotating. The white line was identified while the wheel was spinning. The strobe light was directed towards the spinning wheel, and the strobe frequency was gradually adjusted. The wheel was observed until the white line appeared to be stationary. When the line appeared to have stopped, the strobe frequency was recorded. Multiple subjects were repeated if required, and each frequency was recorded. Part 3 of the procedure involved measuring the rotation of a fan. So firstly, the cover of the fan was carefully removed, and collar tape was then attached to one blade of the fan to act as a marker. The fan was then set to a fixed speed, and this was kept constant throughout the experiment. The lights were turned off to darken the room slightly to make the strobe effect clearer, and the stroboscope was aimed at the rotating fan blade. The strobe frequency was adjusted until the tape appeared to be stationary, and this frequency value was recorded. The strobe frequency was slowly increased, and the formation of multiple stationary images of the tape were observed. The frequency at which each standing pattern occurs for lines 1 to 4 were recorded, and all these values were recorded using a table. The results for part 1 is a video on the observation of water with and without the strobe light. For part 2 of the experiment, the frequency at which the white appears stationary was recorded and converted to milliseconds. For subject 1, the frequency was 47.5 milliseconds. For subject 2, it was 35.2 milliseconds, and subject 3, it was 31.7 milliseconds. For part 3 of the experiment, the frequency of every standing pattern between 1 and 4 lines were recorded and converted to milliseconds. So this was as follows. 1 line gave 23.3 milliseconds, 2 gave 11.8 milliseconds, 3 gave 16.1 and 5.9 milliseconds, and 4 gave 4.7 milliseconds. In conclusion, the stroboscopic motion lab was successfully conducted, and an understanding of how a flashing light can be used to observe and measure the motion of fast-moving objects was achieved. The results demonstrated that when the flashing frequency of the stroboscope matches the frequency of motion of an object, the object appears stationary to the observer. Overall, the experiment confirmed that the stroboscopic effect is a useful optical tool for analyzing rapid motion that cannot be easily seen with the naked eye. It also highlighted how human visual perception can interpret intermittent visual information as continuous or stationary motion under certain conditions.